Well, we're going to have a look today at matrix transformations paradise. Matrix transformations paradise. Now, never a more unlikely title, I hear you say. Never fear, you will see. It is paradise. However, many people think when they hit this topic that they are in matrix transformations hell. And well, they might think so, until they discover the key, the wonderful key to all transformational troubles, which is two simple, beautiful little equations which give us the key. And then particularly when we realise what the matrix equivalent of this key is in a rather more coded form, but easy to unravel, the equivalent matrix form, that's it, then we are instantly transformed into a happy place. Transformed, pardon the pun. And when it comes to matrices, they're in love. However, maybe not just in love, but certainly in paradise. So let's just have a look at some of these matrix questions and see where we go. Now, this is an official exam question, and it had about 4 or 5 parts to it, so I've just picked 2 of those parts out. The first part is just getting our head around what this particular function you can see there looks like on a graph, and then we turn it into the matrixy part, which we will turn from matrix hell into matrix heaven. Here we go. Now, we're just trying to get a handle on it. We have to sketch this thing. Okay, so I've just rearranged it a little bit to get it into a form where I can sort of figure out what's going on here. I can see that it's compared to an original graph of, say, y equals 1 over x, it's been moved up 3, and it's been moved over to the right by 2, and there is a transformation, actually a contraction by a factor of 2, or a dilation of a factor of a half from the y-axis. Okay, now just to get a little bit of a feel for what the function is going to look like, we just sort of go off to the side and sketch it. And that's what I can see that it's going to do. It's up 3, over to the right 2, and there's also a dilation factor, but we won't worry about that for now. That's the general idea of it. Yeah, good show. Now let's get into the main act here on the main axes, and we'll see if we can get this thing happening. There's the 2 asymptotes, the horizontal and the vertical asymptote. Now I'm going to go for the intercepts. So when x is 0, we're looking for the y-intercept. It looks like it's 11 over 4. Express it as an intercept coordinate point. And when we say y equals 0, we're looking for the x-intercepts, and we're going to solve that for x. And that looks pretty good, and that looks even better. And voila, there's our x-intercept, and we'll put that as a coordinate point. And there's one bit of it, and here's the other bit of it. So that looks quite straightforward. We better put our intercepts in, our coordinate points in. There's one of them, and there's the other one. Now, yes, you've got to label your asymptotes. My goodness, you certainly do. Well, is that finished? I think it's okay. Now, the thing for you to make up your mind about is, seeing this as an exam question, or for any other question for that matter, it's a calculator-enabled question. This exam was a calculator-enabled exam. So, would it be quicker to work out those intercepts by hand or by calculator? Well, I've made up my mind. I like them by hand, because the calculator you can do things wrong, and you can put in the wrong keystrokes. If there's simple things to do, I like to do it by hand, as long as it doesn't take me any longer than the calculator. The other thing you've got to consider is asymptotic behaviour. You must make sure that the curve that you're drawing is approaching the asymptotes as the x values and the y values increase in the negative or in the positive. They must not start to swing away again from the asymptote. Otherwise you're going to lose marks. And having done everything that we think we need to do, we better reread the question and make sure we've done everything they asked. Yes, they asked for the intercepts with their coordinates. Did we do that? Yep. And did we write in the equations of the asymptotes? Yes, we did. I think that's pretty good. That's pretty good. I think we're pretty good. Yeah, we are. All right, so that looks like that part of the question is done. Now let's go for matrix paradise. So what have we got here? We've got a transformation such that certain xy points map to their equivalent xy points, transformed xy points. It maps the graph that we considered on the previous page to the graph of the function g of x, where g of x is 1 over x. So this is a bit of a twist. We've got the graph that we just sketched, which was y equals, what was it, 1 over 2x minus 4 plus 3, is now going to be transformed into the graph of g of x equals 1 over x, using that transformation code matrix that you can see there. And it's got A, C and D in it, and we have to figure out what A, C and D are. They're real numbers. So let's just summarise. What is this all about? That is the original function. Now I call it the caterpillar function because it's going to be transformed into the graph of y equals 1 over x, and I'm putting little red primes on those because that is the transformed function, and I call that the butterfly function because the caterpillar gets transformed into the butterfly. So this is a case of what I call backwards transformation questions, where they give you the end result, and knowing the original function, we have to actually find out what the transformations were. Once we find out what they were, we match them up with that code that you can see in the question, and we just work out by equating what A and C and D must be compared to what we got for the key equations. Okay, so yes, that's the code, and that's what we've got to find out. Woohoo! Now here we go. So we've got y equals 1 over 2x minus 4 plus 3. That's the original function, and we're just rearranging it a bit into transformy kind of style. That is the caterpillar or the untransformed function. Now here comes the transformed function, where we're saying that y dashed equals 1 over x dashed. Right. Now, we can now match up the equivalent variables in each of those two equations. That's our butterfly function, yes. Now that is the code statement taken directly from the question above. Okay, now let's just decipher the code into our key equations. Here we come. So now can you read that off from that matrix equation? X dashed equals A times X plus no times Y plus C, and Y dashed equals no times X plus 1 times Y plus D. Did you get that all right? Yes, because that is the key. Da-da! And that is the key to everything. The absolute key to everything. So, let's match up our equivalent statements from each of those two equations, the untransformed one and the transformed one. Yes, those y variables, the left-hand side of the caterpillar function, that's the y minus 3, is equivalent to the y dashed of the transformed function, the butterfly function. And we also know that 1 over 2x minus 4 from the untransformed equation is equivalent to 1 over x dashed from the transformed or butterfly function. Yeah, that's the equivalent statements. Now, let's match those up and see what we get. Okay, so we've got y minus 3 equals y dashed, which gets you y dashed equals y minus 3, and we've got x dashed equals 2x minus 4. Now, that, yes, basically, they are the statements of the key that we have discovered from the original and from the butterfly function. They come from those two equations which I've just labelled above. Now, that's all we need to know. They are the statements of transformation. Okay? Now, but we are told from below that x dashed equals ax plus c. That is from the question, the information that they gave us from the question. Okay? That's the thing with the blue box around it. And also that y dashed equals y plus d. So, it's very obvious to me that if that is the case, and if what's at the bottom of the left-hand column is the case, we can just work out what those A, C, and D numbers are. Yes, A must be 2, C must be minus 4, and D must be minus 3. It's just as simple as that. You see how wonderful the key is? It turns it into matrix paradise. So there's your answer. So that's a perfect example of a very simple backwards transformation question using matrices. Okay? So don't be confused. Just transform yourself into matrix paradise like I did. And you've got to reread the question. Before you leave the question, you must reread the question. Did you find the values of A, C, and D? You did, didn't you? Good. Yes. Well, yes. I'm a maths geek, and so are you. So that's lots of fun, isn't it? Now here's another one, which I picked out of somewhere. And this one is a forwards transformation question, except it's got all kinds of gobbledygook matrix equations stuff put into it. And we're just going to decode that and make it harmless and happy. So that is the key. That is the key in this statement. And they're saying we've got to find something or other. What do we got to find? That is the original equation, that one. So that's my caterpillar equation, or yes, that's right, the untransformed one. And we've got to find the transformed one, or the butterfly one. That's what we don't know. Okay? So, right. Now, just let's put that into a pictorial representation for you so we can just completely work out what we're trying to do here. We've got the caterpillar function, and we are going to find the butterfly function with going on a forwards transformation question using the key that they give us. Okay? We know the caterpillar function, or the original function. We know the key. There's nothing hidden in that key. It's all there. And we have to find the new transformed or butterfly function. Okay? So this is a forwards one. Okay. We substitute, just to make it clear, we substitute from the key. In other words, the key opens up the lock by substituting it into that keyhole, if you like, which is the untransformed function, and it turns the door to get the butterfly function and works it out for us. Okay, that's what we do. So, let's go for it. Okay, there. Now, I want to emphasize with you, there are two ways that you can do this. Seeing this thing is written in this matrix kind of equation way, you can basically do it two ways. There's the easy way, and there's a happy me, because that's the way I like to do it. And there is the hard way, which is the sad, upset me. So, yeah, that's the way I don't like to do it. The easy way you do by minimising the matrix arithmetic, which I don't particularly like. And the hard way is by maximising the matrix arithmetic. So I'll show you how to do it both ways, and you make up your mind what makes you happy and what makes you sad, okay? So here comes easy way, and there's the happy me. So what do we got? We've got this funny looking matrix capital letter kind of equation, which I'm going to get out of as quickly as I can and decode it into just my keys, which I like. Okay, so that's, now what's that saying? That's saying that Yeah, capital X is just matrix of x dashed y dashed, and that's equal to T, which is that matrix you can see on the top right hand corner of the question, times matrix little x little y untransformed plus B, and B is the matrix 1 and 2, as you can see. Now, I'm just going to decipher all that into two key statements. I'm going to simplify that first though. Therefore, we've got, that's the simplified version, and now here we go. I'm going to zap it with some matrix kind of undoings and get what that really means. That's the first statement from the x dashed equals no times x plus minus 3 times y plus 2, and then we get y dashed equals 2 times x plus 1 plus no times y plus 2, and that's what you get. Now that's the key, that's the key, that's the key. Okay, so armed with that, we know that the original caterpillar function is y equals 2x plus 5, and we've got our key down below. So there are some equivalent things. You've got to put the key, turn the key into that door to our butterfly function. Okay, so we know from the key that the y term down in the bottom left hand side, which I've just circled, and in the top right hand side, which I just circled, they are the same y. They're the same y. And also the same applies to the blue circled x terms, which I just also emphasise for you. They are equivalent. So you sub the key into the door. Okay, and that's the door, is the caterpillar function, and you have to get them in a form where you can substitute them, because you have to make x and y the subject from those key equations. There it is, I've rearranged them for you, okay? There they are. Now, here we go, we're going to substitute in now. There it is, into the original equation, and that basically gives us that big mess, which we're now going to work with some algebra to get our butterfly transformed function. There we go. Now we've just got to crunch through it, cancel out those 2's, and just simplify it a bit, and some little bit, I think one more line. Yeah, now I think what we can do now is we can just drop the dashes because we're there. We've got our transformed function. And I'm happy, and it's the butterfly function. Now that's the easy way to do it. That's why I'm happy there. Now let's go through the miserable way. Can you see how happy I look? I look so delighted. That's when you use the matrix arithmetic. Okay, here we go. Fasten your seatbelts. Now, we've got that statement, and I'm not going to decode the statement straight away. I'm going to work with it using matrix arithmetic. That's the key. Yes, that's the key for you and me. And what I'm going to do is I'm actually going to solve it for capital X, which is the key rearranged immediately before plugging it into our original caterpillar equation. That's what you do with this technique. So we sub that into the original untransformed function, the caterpillar function, to get our new transformed butterfly function. So here we go, crunch, crunch, crunch. We've got to work out what capital X is. So you multiply both sides by t, inverse t, and that dissolves the first two terms on the left hand side into the identity matrix, which is just 1, so you can just forget writing that. And that's what we get. Now we've got to get capital X by itself, so we've got to subtract b from both sides. Alright, now that's what gets me my capital X. Now I've got to figure out what to do with that right hand side. Ooh, I've got to work out an inverse matrix. Alright, there's capital T. Now I hope you all know how to do inverse matrices. They're lots of fun, and I just did it really quickly because I'd work it out for you. Now, yeah, it's better to express it that way. So now we're going to plug that back into the equation on the top line there of the right hand column and see where we go with that. Yes, that's right. Now, okay, so far so good. Now I'm putting it into more uncapital letter type language, the language that we understand, matrix language. And I'm going to solve that, decipher the matrix statement, therefore, little x and little y, just immediately before I plug them into my caterpillar untransformed function. There's x. Now you see if you agree with me. Is that what that line above says in regard to x? I think it does. Yes, it does. And y is also similarly worked out. Okay, you got it? Okay, we're nearly there now. Yes, that is the rearranged key. Okay, the two equations. So we're going to put them straight into our, from there into our caterpillar equation, our untransformed function. Okay, so here you go. You ready? Big mess. Yes. Okay, so that's what I've done. I've plugged them straight in. Now we've just got to fiddle around with that and get our equation looking a bit more reasonable. Y dashed in terms of x dashed. And it should work out the same as what we got before. Yeah, we're cancelling the 2's out. And yes, and I think we're just going to add 2 to both sides. Yes, and there it is. Now that's it. That's the same as we got before. But it was considerably less pleasant. That's my opinion. Hope I'm not putting all you matrix lovers off here. We're going to drop the dashes because we're finished. And that's our transformed function. And look how much fun I had doing it. So that's it. I think that's the end of the show. So I hope by me showing you first of all the backwards transform technique and the forwards transform technique using matrices, that you too have entered matrix paradise. Thank you so much for listening, and we'll see you next time.